1 half natural log x.
Yes.
And I'm not assuming that x is positive or anything here. Plus c. Yeah, the other thing is I could have left a 2 on the left side with a v. It would have been just v squared equals natural log x. But multiply both sides by 2, it knocks those out anyway.
Yeah.
So you get v squared equals natural log x plus, I'm going to call it c1, where c1 is just equal to 2 times whatever c is. Okay. And now, we've almost got this, except that the v, hiding behind v, we did a substitution. V is equivalent to y over x. Right? Okay. And then finally, if I multiply both sides by, x squared, we can get y squared equals x squared times natural log x plus c1, whatever you want to call that constant. Okay. So this is in implicit form. We could leave it here, just leave it in implicit form because we don't know if this represents top half and bottom half of a curve, and the one that we want would be specified if I knew an initial condition, if y were positive or negative.
Oh, it's y positive or negative.
Right. Because if you square root both sides, y can be positive or negative and satisfy if you get, it's always positive, but y can be positive or negative. So this represents the top and bottom half of a curve. If you graph that, you wouldn't get a single function, you'd get 2. So which one you want would depend on the initial condition that you got. So this is the general solution. Okay. All right, so that idea of doing a substitution when it's a first order, when we have a first order differential equation, where I can somehow get the right side, if I can recognize the right side, and not just a function of x, but a function of y over x, and then we could make a substitution, v equals y over x, and go from there. And hopefully we can transform that into linear or separable differential. Okay.
Does that technique work for things more complex than y over x? Maybe you can figure out
I imagine it should. Yeah, and why they picked, why bother cataloging this particular? That seems rare and almost arbitrary that we pick y over x. So part of what we're doing the first few weeks definitely, and a lot of it is cataloging different types of equations, getting a collection of a lot of different types that we can solve. Okay. All right, so very calculus heavy, obviously. We're back to calculus, integrals, things like that, derivatives. Okay. Let's do another example of this type. Okay. All right, so say we got the equation x minus y prime equals x plus y. All right. So, well, in that form, it's not immediately, can't tell that it's separable. It doesn't look like it is. But again, if you divide both sides by that x minus y, we get dy dx equals x plus y over x minus y. Okay. Now this is absolutely not separable. There's no way to factor and get these x's and y's, pull them apart as separate factors. So note, this is not separable, nor is it linear. Okay. One thing we can, one thing we can do, this is a trick. And again, where do they come up with them? It's a good question. I'm going to factor an x out of the top. I just said we couldn't factor it though. But if you factor an x out of the top, I do get 1 plus, not just something involving y, but y over x.
Beautiful.
See that? Do the same thing to the bottom. Factor that x out of there, and then I get 1 minus y over x.
So we can do the substitution as long, even if we have forms of x and y, or of x that are not x, y over x?
Right. Well, it probably would work as long as they're all the same. If it's a function of whatever it was, I don't know, natural log y over x. If they were all appearing like that, all the appearances of the variable were like that.
Sure. Oh, so
So-
all the appearances of the one you're making the substitution
Yes.
for have to be,
So it's a function of just this expression alone. In fact, so in that equation, it should only involve any appearance of variables should be y over x, wherever they appear.
gotcha.
I guess that's what makes it homogeneous. They all appear the same when they appear. Okay.
But is
So-
that's only applicable to the dependent variables.
What's that?
Well, if you have the independent variable there outside of that term.
Like crossing the stuff out.
Oh yeah, the independent variable goes out there, but it's still,
Oh, yeah,
it's still
sure,
there.
it's cancel out.
Okay. Now this is certainly, yeah, it's not separable. It's not quite linear because here's one way. Here's how you can tell it's not linear. You can rewrite this as dy dx. If I wrote this as 1 over 1 minus y over x plus yx over 1 minus y over x. Subtract that over to the other side. Well, yeah, no, it's not. Right, never mind this part. It's not linear in y. Okay. All right, but we do have this expression here, y over x, everywhere the variable appears. So this is an expression, this is a function of just y over x. Okay, so we make that substitution, and this is just, like I said, akin to U substitution. It's a change of variable technique. V equals y over x. Okay? So that, again, y is just x times v. And this will be the same every time. And dy dx, using the product rule, derivative of the first times the second with respect to x, will be v plus first times the derivative of the second with respect to x, dv dx. Okay, and we substitute that in where I see dy dx. Okay, and I'm just going to mark this one as star, just for reference. Second step. So that equation will become, actually it should be this one. So that equation now becomes, I'm going to replace dy dx with this. It becomes v plus x dv dx equals 1 plus v, 1 minus v. Okay. Now, I'm going to subtract that v from both sides. And what do we get? X dv dx equals 1 plus v, 1 minus v, minus v. I'm going to multiply both sides of this by the denominator, 1 minus v. Okay, so we'll have, imagine multiplying the whole thing by 1 minus v. We're going to have x, 1 minus v dv dx equals, we'll cancel out here, I'll have 1 plus v minus v times 1 minus v. So I just multiplied both sides by 1 minus v. It hit here, canceled out there, and got 1 over that side. Okay. Now, following through, multiplying that out on the right, I got 1 plus v minus v times 1, that's nice, and then minus, that's plus a v squared. Those cancel out. Alright, so, writing this one more time before we separate, we got 1 plus v squared. And now, I get that 1 minus v, if I get that back to the other side, what do we got?
Squares that we. No, not quite. No.
It is inseparable.
Yeah.
But on this side, when I get that over the other side, I got to multiply by the reciprocal. So we're going to get, okay, multiply both sides by 1 minus v over 1 plus v squared dx, both sides, and 1 over x. We're going to have 1 minus v, 1 plus v squared dv equals, multiplied by dx and dx over x. Right? Okay. Now we integrate. And what is, oh goodness, what do we do on the left?
U equals 1 minus.
It could be, yeah, I could break this apart. 1 plus v squared minus v over 1 plus v squared. Break that apart. I mean, a calculator would also handle that integral or something like that. Integral 1 over x dx. That's just going to be natural log x plus some c. Now on the left side, 1 over 1 plus v squared, integrating with respect to v, arctangent. Minus, and what about this guy? There would be a u substitution involved. If u is 1 plus v squared, then up top you got almost derivative of that. But you have 1/2 of it. So if you follow that through, I think you get 1/2, and that's a natural log 1 plus v squared equals natural log x plus c. Okay. That's a, well, you know, my original solution, we can transform back and get the v's out of there. And this is going to be arctangent, or tangent inverse, however you want to write it. 1 plus, what was v? Y over x squared minus 1/2 natural log 1 plus y over x squared. Leave it here. Okay. Or multiply both sides by 2, get rid of that fraction. That's as far as I want to go. Yeah.
Why didn't you reduce the when you have the 1 plus v squared? Why didn't you do the difference of squares there?
Where at?
You have 1 plus v squared over 1 minus v.
There.
Can you pull the 1 out of the bottom and then reduce?
Pull the 1 out of the bottom.
The negative 1 out of the bottom and have it negative
v
1
plus
times
1.
v plus negative 1 times v minus 1.
It would be negative. Oh right. Okay. V minus
Reduce
1.
more.
I don't know, but it's not going to cancel with anything. V minus 1. Oh, the top doesn't
squares, it's a v plus.
the top doesn't factor. 1 plus v, 1 minus v.
Yeah.
That'd be
You
right.
multiply both sides by 1 minus v, and then you'll have 1 plus v squared. Then can't you just subtract v squared? And be left with on the right side.
Yeah, there might be another way of getting around it. I move things around a lot and then move them back to integrate and to put it in separable form.
If you multiply both sides by 1 minus v, then just subtract the v squared. You'll have
Where at?
Right there.
No, but how do you get the x back to the other side?
You have a 1 on the right side still, so then you can divide by x or multiply by
Yeah, but divide by x, leave it x in the denominator, and the 1 plus b squared.
Oh, that's true.
Yeah. So this is, I would want, you can't solve this for, you cannot solve this for y. This is one that's impossible. Okay, don't, yeah.
Just solve it for x. Change the dependent variable.
Why does it end up as arctangent of 1 plus b squared? Would it just be arctangent of b
Where at?
at the
Yeah.
second?
Oh, wait, that's arctangent v, right?
Yeah.
Right. Yep. That's not, I don't get the whole thing. No, right. Yeah, 1 over 1 plus u squared integral of that is just arctangent u. Good call. That's just v, arctangent v. And so this would just be y over x, right? Okay. That's right. That one's correct. That's the natural log, that whole thing, because that's its derivative sitting up there, but half of its derivative. Okay. All right, so we're going to leave that one there. And that is, well, that's the homogeneous part, okay, of 1.6. 1.6 is a long section, a few different techniques. All right. Now, Bernoulli is the second part of it. So Bernoulli equations, Bernoulli equations have the following form. dy dx plus, this is the one, we wrote it down at the beginning. I said, oh, it looks just like the form of a linear first order differential equation. Except for one difference. I got this y to the n right here. Okay, so I'm going to call this just equation 1. Now, note for a second, if n equals 0, that's the power on the y. If it's 0, then what do we got? Y to the 0 would just be 1, and that would just be linear. We would do it that way. So it contains linear as a special case. If, on the other hand, these are special cases, if n equals 1, if y is 1, the exponent is 1 here, then I got just factors of y on the same side. I could bring that px y over the other side, factor out the y, and that would be separable. Okay, just to show what that would look like, if n equals 1, then we'd have dy dx equals, I can factor out a y on both sides, and it would be q of x minus q of x. And that's just one big giant expression involving x. That would be separable. Okay? So we're going to consider when n is not 0 or 1, because we have other methods of solving it. Okay. All right, so the approach, when we have that, there is a way to transform this so that the result will be linear. Okay, it's close to linear, but not quite. So the approach is similar. It's going to be a substitution, but not the y over x business. What we're going to do, and don't ask me where this came from, who thought of this? I don't know. Bernoulli. We let y equal 1 minus n. Okay? Now I'm going to follow through a little bit on just the general equation, and then we're going to do a specific example and see how it works out.
Let y equal 1 minus n?
Oh, pens. Yes. Let v equals y to the 1 minus n. Sorry. Get rid of this whole sentence. All right. Let v equals y to the 1 minus n. There we go. So it is a substitution. Now, if this is the case, and you guys don't, this will be in the notes, you don't need to know the derivation, so you can put down your pencils if you like. dv dx, if I derive that in terms of x, okay, y is a function of x, then what we get is, well, I would use the power rule in conjunction with the chain rule. The 1 minus n comes down, times y to the 1 minus n, well, drop that power down by 1. 1 minus n minus 1 times dy dx, right? So this would be 1 minus n, and the 1's cancel out. This would be y to the negative n dy dx. Okay, that's dv dx. Now, you can solve this, kind of turn it around, and isolate the dy dx. Okay? Isolating dy dx would yield, multiply both sides by y to the positive n power, and divide by 1 minus n. So we have dy dx. Follow that, multiply both sides by y to the n. They would add and give 0 there. So we'd have, and divide by 1 minus n. So we'd have y to the n, 1 minus n times dv dx. Okay. Now what we do is substitute that in to equation 1, replacing dy dx with that. Okay, this is the theory. We're going to do particular examples. And let's just start right here. So equation 1, replace dy dx with this. Y to the n over 1 minus n dv dx plus p of x y oh, and I'm going to replace y with, oh, right, we got to solve that for a second. Hold on. P of x y equals q of x y to the n There's one step missing. Okay. Now, all of this right here we recognize as 1 over y over n around dv dx. We just substituted that. So, where's the step that's missing? Y. Dang it, I don't remember where that comes from. Anyway, this business right here is y. If you solve this, let me see here, y to the 1 minus n, yeah, this is what I'm going to do. Y to the 1 times, that's y to the first, not y prime. Y times y to the negative n equals v, which means if I solve this for y, this becomes y equals, divide both sides by y to the negative n, that's the same as multiplying by y to the n, that becomes v y to the n. Okay, so I replaced the y with v y to the n right there. Okay, that's the missing part. Okay. Now the dy dx from this part, that is right here. We've replaced that. Now if I solve this for dv dx, or isolate it, I'm going to multiply all sides by 1 minus n. And at the same time, multiply by y to the negative n. Yes, that's how it happens. So, see all these y to the n's? If I multiply or divide both sides by y to the n, those all cancel out. At the same time, multiplying by 1 minus n, we get dv dx plus, and 1 minus n is going to hit all these, 1 minus n p of x v. Oh, wait. Yeah. Because the y to the n, when I divide by it, it cancels that out. That becomes v equals, this derivation is rough, the 1 minus n goes to all sides, so the right side is 1 minus n. That cancels out q of x. Okay. Now, all that derivation shows, don't memorize this. What that derivation shows is that now, this equation, whatever n starts off as a constant, but this is a function of x alone. This will be a function of x alone when I know that power n, and it's linear in v. Okay, so that's what the big picture is. We took this equation and we transformed it and it becomes linear in v. Okay. And then once we do that, when we do that transformation, we could use an integrating factor. Yeah.
So you needed the integral.
Mm-hmm. Okay. So we'll do one example 1, 2, 3. Say we have the equation 3xy squared y prime equals 3x to the 4th plus y cubed. Okay. So, isolating y prime here, if I divide by 3xy squared everywhere, I'm going to do that just so I can see it. 3xy squared. The 3's will cancel out. I'll have, what, x cubed over y squared. Plus, the y's cancel out, leaving 1 up top. I got 1 y over 3x. Okay. All right. Now, this is certainly not separable. Just to keep pointing that out. And it's not linear because I got a y in the denominator. Okay. But I do have a y right there. I'm going to bring that over to the other side. Minus y over 3x equals x cubed y to the negative 2. Okay. Now, we're close to recognizing this. Y prime minus, this is 1 over 3x y to the first equals x cubed y to the negative 2. So this is Bernoulli. This is p of x. This is our q of x. And n is negative 2. So this is Bernoulli. With n equals negative 2. All right, so let's go with, just for the sake of time, I'm going to put it, so n, this is what we do, the transformation that takes a Bernoulli, first order Bernoulli equation and transforms it into a linear one with respect to v. We put n equals 2 in that. negative 2. Okay? So basically, with v equals y to the 1 minus negative 2, that's our n, we get, after transforming that, we'd have dv dx plus, what's 1 minus negative 2? That's my n right there, times p of x, negative 1 over 3x, times v equals 1 minus n, and n is negative 2, times q of x. And our q of x in this function is x cubed.
Shouldn't it be Vy here?
What's that?
Shouldn't it be Vy here?
No, I'm using this.
Oh, okay.
Our
okay,
q of
okay,
x was
okay.
x cubed,
Yeah,
and there's no more y's over on in that form.
right, okay, so
Yeah.
we're doing the last one.
Okay, so one more simplification here, dv dx plus 1 minus negative 2, I get 3, but this would be, oh, it would cancel with that 3, so I'd have minus 1 over x v equals 3x cubed. Okay, so this is linear in v,